This lecture is going to talk about polytropic processes and ideal gases. So these are two concepts that we've talked about earlier on in the course, and I want to combine them together. In other words, I want to talk about what does a polytropic process look like when the substance that we're working with is an ideal gas. So realize these are two different things. An ideal gas is a characteristic of the substance, and a polytropic process is a description of the process that that substance is going through. So we're going to combine these two things next. So first of all, a reminder of what a polytropic process is. Polytropic process follows a particular path on a PV diagram, and that path is given by this equation. PV to the n is equal to a constant, and n, of course, is a polytropic index. So when we have a process that goes from point 1 to point 2, or from state 1 to state 2, P1 V1 to the n has to be equal to P2 V2 to the n. Polytropic process. Now we can rearrange that equation and show it as a ratio of pressures. So P2 over P1 is equal to V1 over V2 raised to the power n. So we've just moved all the pressures onto one side and all of the specific volumes onto the other side. So far, this is just a polytropic process. So if we have a substance undergoing a polytropic process, it follows this relationship between P and V no matter what. So it doesn't matter what the characteristics of the substance are. This is the path that it's following on a PV diagram. So that's a quick review of polytropic processes. Next, I want to review the ideal gas law. So that's PV equals RT. So notice the ideal gas law also involves these two properties, PV, that are in our polytropic process. So we're going to combine these things together and show some special relationships that we can use if we have a polytropic process and an ideal gas. So I'm going to take the ideal gas law and just rearrange it. So notice this is still just the ideal gas law, but I'm going to evaluate it at point 1, the beginning of our process, and at point 2. So all I've done here is taken this equation and divided it by temperature. So P1 V1 over T1 is equal to R, and of course that's going to be equal to P2 V2 over T2. So for any process, doesn't matter whether it's polytropic or not, if we're dealing with an ideal gas, then PV over T stays constant. So here PV to the n is a constant, and for this substance PV over T is a constant. So what we're going to do is combine these two things together. So notice this relates pressure and volume. What would be very useful, as it turns out, is an equation that relates pressure and temperature. So what we're going to do is use this equation to eliminate the volumes from that equation and get it in terms of temperature and pressure instead. So first of all, we take this equation, get rid of the R in the middle, just equate that, and rearrange it to get V1 over V2. In other words, something ready to substitute into there. So if we take this and rearrange it, we get V1 over V2 is P2 over P1 times T1 over T2. So that's still just the ideal gas law. That's valid for an ideal gas going between any 2 points. The volume ratio has to be equal to pressure ratio, P2 over P1, times the temperature ratio, T1 over T2. Remember, these temperatures have to be in degrees Kelvin. Now we're going to take that and substitute into the polytropic expression. So P2 over P1 is equal to, so we've just taken that and put it in where V1 over V2 used to be. And so now this is an equation that combines the polytropic process with the ideal gas law. So this equation is only valid if we're looking at a polytropic process and if the substance is an ideal gas. Now it turns out that in this particular form it's a little bit cumbersome, and the reason is that the pressures appear in 2 places. So we want to rearrange this a little bit so the pressures only appear in one spot. Well, we can do that. We divide both sides of this equation by P2 over P1 to the n. So it's eliminated from the right-hand side, and over here we would then have an exponent of 1 minus n on our pressure ratio. So now we have pressures only on this side and temperatures only on this side. So this relates the pressure ratio to the temperature ratio. Now the last thing that's typically done to this equation is to get it so that there's this exponent involving the polytropic index on only one side. So we'll take the 1 minus nth root of this. In other words, we'll raise both sides of this equation to the power of 1 over 1 minus n. And when we do that, we get this. So now we just have our pressure ratio and our temperature ratio to the n over n minus 1. Notice the little trick that's happened here. This has been inverted. So it's T2 over T1, just to get it so that it's P2 over P1 is equal to T2 over T1 to get these in the same order. And because I've inverted this, I switched the sign of the exponent. So that's how 1 minus n became n minus 1. So this is the final expression we're after here. It relates pressures to temperatures. But we have to remember that is only valid for an ideal gas undergoing a polytropic process. So just to summarize this, we really have three equations here actually. This is our original polytropic expression. So if we're relating pressures to volumes for a polytropic process, then that's true for any polytropic process. That doesn't matter what the substance is. So this pressure ratio related to this volume ratio, any polytropic process, regardless of the substance. However, if we want to relate either of these things, either the pressure ratio or the volume ratio, to the temperature ratio, this part of this is only for ideal gases. So if we relate P to T using this equality, we can only do that for ideal gases because we use the ideal gas law to get that connection between temperature and volume. So these are very useful expressions, but it's critical to remember that this part can only be used for an ideal gas.